In this short video, we're going to be going over how to minimize a firm's costs in the long run. That is, find the combination of capital and labor which lead to the lowest cost of producing a given level of output. And we're going to start by doing this graphically, and you're going to notice that the graphs are going to look very similar to the indifference curve graphs that we drew in the last couple sets of lectures, but it's not going to be exactly the same, and I'll explain exactly why. So we're going to start by drawing what we call isoquants. An isoquant is going to depict all the combinations of capital and labor that result in the same total level of output. Okay, so this isoquant here might reflect all the combinations of capital and labor that result in the same total quantity of output, or sort of the final product. It could be something like cars or cell phones or something like that. So let's say that this isoquant corresponds to 10 units of the final output. And that implies that, relatively high amount of labor and a small amount of capital could yield this 10 units, or a relatively high amount of capital and small amount of labor. Okay, and then there might be other isoquants on this graph that correspond to higher or lower levels of output. And we'll assume that isoquants that are further up and to the right correspond to higher levels of output. And isoquants that are sort of further towards the origin correspond to lower levels of output. Okay. Now we're going to assume that these are convex shaped, which is going to reflect the assumption that there's diminishing marginal productivity of a given type of input. So for example, as you hire more and more labor, each unit of labor is a little bit less productive than the last. This may or may not be true depending on the context, but we're going to assume it's true. And the intuition could be, for example, that as you hire more and more labor without adjusting the capital, that the different workers are actually sort of waiting in line to use a given piece of capital, which is slowing them down, making them less productive. Okay, so that explains this convex shape. And again, we're going to assume that more of the two inputs results in higher levels of output. So that's why isoquants that are further up and to the right correspond to higher levels of output of the final good. Okay, the next thing we're going to do is we're going to add what's called isocost lines to this graph. Okay, so we can start with the cost function. The cost is a function of capital and labor, and that's just equal to the price of capital times the amount of capital used, plus the price of labor, or the wage, times the amount of labor used. I'm actually going to erase this and say, let's suppose that this is some particular cost. It could be like, $100 or $50 or something like that. I'm just going to call this the cost. This is just going to be a constant. And what we're going to do to derive the isocost line is we're going to rearrange this equation to solve for the amount of capital. So we're going to get that capital is equal to some cost divided by the price of capital plus the wage rate divided by the price of capital times the amount of labor used. Okay, so this is basically going to allow us to plot all the combinations of capital and labor that have the same total cost. It could be something like $100 or something like that. Okay, so let me draw this isocost line in blue. So in the consumer's utility maximization problem, they were trying to find the highest indifference curve that still touched their budget line. In the firm's problem, we're actually trying to do the reverse. They have some level of output that they want to produce, let's say 10 units, and they're trying to find the cheapest way to do that. So what they're actually trying to do is they're trying to find the lowest isocost line, lowest blue line, that is just tangent or just still reaches or touches the isoquant. Okay, so it's still going to be, the optimal level is still going to be determined by the point of tangency, but rather than trying to find the highest isoquant, they're actually trying to find the lowest isocost. So now, just like we did in the consumer's problem, we're going to use this graphical analysis to help us derive a couple useful relationships. So in the consumer problem, we had to find the marginal rate of substitution, which gave the trade-off of the two goods that left the consumer indifferent between before and after the change. For this problem, we're going to define something similar, but rather than the marginal rate of substitution, or MRS, we're going to define the marginal rate of technical substitution, this T here, as the change in the two inputs that leaves the amount of output of the final good unchanged. Okay, so it's going to be the absolute value of the change in K over change in L that leaves the output unchanged. And not surprisingly, the marginal rate of technical substitution is equal to the absolute value of the slope of the isoquant. I'm going to tell you that the marginal rate of technical substitution is going to be equal to the ratio of the marginal products of the two inputs. So marginal product of labor over marginal product of capital. Again, on the left-hand side, over here we have the change of capital in the numerator, and on the right-hand side we have the marginal product of labor on the right-hand side. And the intuition is basically the same. If you need 2 units of capital to replace 1 unit of labor, leaving output unchanged, then labor must be twice as productive as capital at the margin. Okay. So that's the first relationship. And then the second relationship is I'm going to tell you that this is going to be equal to the ratio of the prices of the two inputs. That is the price of labor, which is depicted by W, divided by the price of capital, which is depicted by the letter R. Right? And the intuition for this is going to be analogous to the intuition for why the ratio of marginal utilities was equal to the ratio of prices for the products in the consumer problem. Okay, so to show this intuition, let's rearrange this equation. And we'll rearrange it to show that the marginal product of labor divided by the wage rate is equal to the marginal product of capital divided by the price of capital. Basically, what I did is I divided both sides of this part up here by W and multiplied both sides by the marginal product of capital. So let's look just at the left-hand side. It has the marginal product of labor divided by the wage. That is telling us how much is produced, about how much output is produced per dollar spent on labor. Right? Suppose that additional unit of labor produces 10 units of output and the wage is 5. If we divide 10 by 5, then each dollar spent on labor produces 2 units of output. And on the right-hand side, we have the marginal product of capital divided by the price of capital, or said another way, at the margin, it's the amount of output produced per dollar spent on capital. And if the firm is optimizing, if they're minimizing cost, the amount produced per dollar spent on labor should be equal to the amount produced per dollar spent on capital. Otherwise, they should shift their production towards the input which is more productive per dollar. So that wraps up this video. In the next video, we'll look at how to solve these types of problems using calculus-based methods, using the math optimization tools that we've been using in the last couple sets of lectures.